So this is a nice example from the book. It's called Machine Learning by Peter Flach. I would say that this is, one of the advanced textbooks on machine learning. It's not like level A. So in this textbook, the slides are available online. So I will share with you the PDF slides for this textbook. They are like very neat, filled with maths, but you guys can have a look at them. So there are more than, I think, about 200 or more slides. So actually, the book is right here. The slides are right here. So yeah, so you have like like about 500 slides in the explaining the textbook basically. Okay, so let's look at these two examples now in a very simple and intuitive way. So what do we have? The first case here, we have 3 points, 2 negative points belonging to, let's say, class 1, and 1 positive sample belonging to class 3. Okay, so we are in a 2-dimensional space. So each, of these points, each of these samples, x1, x2, and x3, they have 2 features. Okay, now when we want to solve, if let's say we have, derived all the maths, we solve this problem. So what we're looking for this hyperplane that maximizes the margins between between these 2 classes. And look, so this is the first case. We have only three point samples. This is, the direction. This is the vector that we found. So this is the W. Actually, this is the W star. Okay. So the optimal parameter, and it's perpendicular to the hyperplane, and we can compute them. We can, find basically compute the margin directly just by looking at this case. Now the second case, right here. So we added only 1 point. So this is the point that we added. So we added only 1 data point, a positive sample. And what do you guys notice? Just by comparing these two. So when we added the new training sample, just 1 point, you can see that the hyperplane, the direction has completely changed. So the W rotated, right? And also the margin decreased. Okay, so here it was much larger. Okay, so this is a narrower margin. So you can notice just by comparing these 2 examples that minor changes in the training data set might lead to completely, generating different classifiers. Okay, so this is why your training data, there is a whole lot of work on, how to perform there's what we call sample selection, for example. So learning how to select the best samples, the best training samples that you can rely on to solve your problem, because not all of your samples might be good, okay? So this is one thing to keep in mind. And also you might think, well, maybe in this case it's more generalizable, because now we know that, if the green ones might be located in this part, not just, below this hyperplane, okay? Great, so let's look at this more. So where are the support vectors? So if you remember from the previous lecture what we learned. So if you look at this, generally the support vectors, they lie on what? On the hyperplanes, the marginal decision boundaries, right? So here we have 3 potential or candidates. So 3 potential support vectors, okay? And in this case, we have also 3, okay? But what I would like to tell you guys that not all support vectors, and we're going to discover this later on, not all samples which lie on the marginal hyperplanes, they will be selected by SVM as support vectors. So at least generally we only need 2. So if we have 2, we can find the margin, we can define, our hyperplane. So at least we need 2, but if we have more, that's fine, but we don't need to pick every single point that is on the marginal hyperplane. Okay, cool. So this is number 1. Then also, so this is what we looked. So by adding a second positive sample, this caused the boundary to rotate and the margin to decrease to 1. So now let's look at this first simple example. So we're going to focus on just case 1 from now on. So here, when just visually inspecting the figure, I would like you guys to compute the margin L. okay? Write it down. And also the norm of the W that you get. And so I already answered this. So how many potential SV support vectors we have? So we have 3 potential samples, right? X1, X2, and X3 because they lie on the hyperplanes. But what is the width of the margin? So this is, 1, 1, 2, okay? So just, using the units of this plot, you can see that the margin is equal to what? L? 4, right? 4 units. So then in that case, W is 2 divided by 4. That's 1/2. Okay? So this is, just based on visual inspection. Now let's get to the real thing and start working out all the maths on this example using Lagrangian. So if you guys remember, so I'll walk you through the different steps. So there are like a few steps to follow to solve this. And remember, the first one is solving the primal problem. So to solve this constrained optimization problem based on our training set, so the train set that we have is composed of only 3 training samples. Okay? So the first thing would be to define the Lagrangian. So we have defined this previously. And also expand it. So we expanded it. Now what I would like you to do, guys, is to write it down mathematically. So just as a good, reminder for you, so I would like you to blend this, apply it to this particular case, okay? So you have only 3 points and expand it. And actually what you have, you will replace the W with its components, with this vector, W1, W2, okay? So I'll give you a minute, pen and paper, and write it down. Okay, so we can do this together. So basically we have W transpose times, so this is just the norm, the squared norm of W, right? Minus, now we have alpha 1, so negative, like alpha 1 times y1. y1 is negative, right? So negative times negative, because we know that this is a negative sample, right? So then it's plus alpha 1. And x1 transpose, x1 is like 1, 2. And we have w1, w2, right? And then we have then minus alpha 2, and y2 is negative, so plus alpha 2. Then we have transpose x2 transpose, so that would be this vector, then w1, w2, right? And then we have alpha 3, and y3 is actually positive, so that's minus alpha 3. Then we have x3 transpose minus negative 1, negative 2, right? w1, w2, right? So that is this term. So if we write it down like in a simple way, so that would be, so all of this, right? So w1 squared plus w2 squared, right? Plus, now let's write it down. So here we have alpha 1 times w1 plus 2 w2, right? Plus alpha 2. So we have negative w1 plus 2 w2 minus alpha 3, negative w1, negative minus 2 w2. So we stop right here, okay? Then we can continue. So this is plus something, okay? So we will continue right here, plus. So we have the b times what? So we have alpha, negative alpha 1, right? Because this is, y1 is negative, so alpha 1 minus alpha 2 plus alpha 3 plus alpha 1, the last term we just expanded, and this is our Lagrangian, okay? So now what is the next step? Now that we have computed this, okay, what we need to do, we need to compute the partial derivative of the Lagrangian with respect to its primal variables, okay? So here, this is the formula that we got. So this was just an exercise for you guys, but we solved it like for the general case, so now we can just blend it in directly. But alternatively, you can derive this, you know, for this specific particular case and get your W, but we're going to use the general formula that we got from the previous lecture. So what I would like you guys to do is like to transform these two constraints, translate them, these two constraints A and B, based on this particular data set, okay? So you can write the W star, and here we have only 3 points, right? So let's write it down together. So this is very easy. So we have, you know, we have negative alpha 1, and then x1, the first, negative alpha 2, x2, and plus alpha 3, x3. So what do you guys notice? This is just a linear combination of what? Of the training samples. So this is exactly in a linear combination weighted by the coefficients alphas. And then when you sum all of those vectors, what you get? You get a two-dimensional vector, right? So you know that your W star should belong to R2 because it's a linear combination of two-dimensional vectors. Now, the last condition that is very important is we have negative alpha 1 minus alpha 2 plus alpha 3 should be equal to 0, okay? So this is an important constraint or equality. So using these two, what is the next step if you guys remember? Now we solve the primal problem. So we found our conditions, right? So next we need to plug these back into the Lagrangian, okay? Substitute and update the Lagrangian to maximize it. So this is the next step, right? So here what we have, we need to define the dual problem to solve. So we want to maximize over all alphas the Lagrangian evaluated at optimal points that we got by, these are derived from the primal problem solution, okay? And it's subject to this constraint. So this is, you know, our constraint. So we need to solve it. And also we know that all alphas should be positive. Okay, they cannot take negative numbers. Now I can rewrite this in a simple way by expanding it. So I just replaced the Lagrangian with the updated the Lagrangian when plugging in the solutions from the primal step, and we got this, right? Now, what I would like you guys to do, I've written it down right here. So we want to maximize this quantity, right, for our training set. So as you can notice, this is very, this is what we discovered last time, is like that the Lagrangian that we want to maximize to find our multipliers that will lead to our optimal W. It all depends on what? On pairwise, inner products or dot products between training samples. So what this inner product does, it basically tells us about the similarities between two samples. And this is important. Let me just, remind you. So if we have two samples, right? If two samples are, let's say, collinear, their dot product will be very large, okay? But then if it's in the other direction, it will be negative. So this is, kind of the max, and this is the min. And here, they are completely dissimilar if they are perpendicular. So you have x, this is sample z, and this is, let's call it, or maybe, okay, x1, x2, and x3. So here the dot product, what it's telling us, it's trying to capture the relationship between, all the samples, all pairs of samples, their similarities. Because generally, intuitively, if you look at this case, so if you have a bunch of trees, right, something like that, okay, and then you have, let's say, faces. So you would expect that the dot product between these two samples, okay, you would expect that you would expect it to be larger, right? Because they're more similar. And if you take, the dot product between cross classes, they would not be. It will be like smaller. So the dot product is basically enables us to explore these similarities, and modeling and understanding how to define similarities between training samples, it drives, a lot of machine learning applications. We can learn those, we can use, more advanced mathematical tools, but the most intuitive and basic one is the inner product between the two vectors, okay? So I'll just give you also another minute, and I would like you guys to write this down, okay? Expand this, because now we need to solve it. So to maximize it, to derive it with respect to the alphas, we need to write down the explicit form of the dual Lagrangian, okay? So we're maximizing it. I just, to make it simple, I introduced the dot products between pairs of samples, okay? So I would like you guys to write it down, because you're going to derive it later on and solve the linear system. Just, at least do the beginning, okay? So I have double summations. Okay, so if we do the first term together, it's quite easy. So here, just, fixing the I and varying the j, so you guys know how to do double summations. So here, let's write the first term. So for I equals 1 and j equals 1, we have alpha 1 squared, so alpha 1 squared, and then y1, that's a positive number, plus 1. And then we have the norm of x1 transpose x1, so that's 5. And then the second term, so let's do a plus. So we have alpha 1, alpha 2. Then we have y1, y2, so that's also positive, right? And then x1 transpose x2, so that's 3. And then the third term, so we have alpha 1, alpha 3, and then it's a negative number now because we're multiplying these two, so it's minus, right? And then we have x1, x3, so that's negative 5, so that would be plus 5, okay? So plus 5, alpha 1, alpha 3. And you guys can keep expanding that, like all the summation elements. And the last term is quite easy, so it's alpha 1 plus alpha 2 plus alpha 3. And if we do that, we're going to get this. So this is what we'll get. Right, so I think I made a mistake, right? Did I make a mistake, guys, for the first term? No. Right, so alpha 1, alpha 2. X1, x2, right. Oh no, so here they gathered everything up. So here, after grouping all the terms together, we will get this Lagrangian. And what do you guys notice? That the dual Lagrangian now only depends on what? Alphas, right? That's why we want to, so all its variables are just, the multipliers. And we have this condition that we had before that we're adding here. So we know that this is, negative alpha 1 minus alpha 2 plus alpha 3 is equal to 0. So what we can do, we can eliminate one of the variables, for example, alpha 3 by replacing it with alpha 1 plus alpha 2. Right? And then we can update the Lagrangian. And now you guys can notice that our Lagrangian depends on just two alphas, right? Alpha 1 and alpha 2. So if we get to solve that, then we can automatically compute the alpha 3 as it depends on alpha 1 and alpha 2. Now, the next step would be to basically solve the dual problem. And to solve the dual problem, what we need to do is to compute the derivative with respect to all parameters, which are alpha 1 and alpha 2. So we compute the derivative of the Lagrangian with respect to alpha 1 and the derivative of the Lagrangian with respect to alpha 2. We set them to zeros. And if you do this, if you derive this with respect to alpha 1, we will get this equality, right? And when deriving with alpha 1, of course, alpha 2 will be fixed, so that's considered as a constant. And then we derive with respect to alpha 2, and we get the second equation. Now we have two linear equations to solve with two variables, so it's pretty straightforward. So if we take alpha 1, like we derive alpha 1 from the first equation and write it in function of alpha 2, then we plug it in, we just substitute it in the second equation, we get that. Just after solving this manually by hand, you get that alpha 2 is equal to 1/8. And then what is alpha 1 equal to? Guys, can you do it now? It should be very straightforward. So alpha 2 here, we have, alpha 1. It should be equal to what? 0, right? And then you have alpha 3, it's alpha 1 plus alpha 2, so it's equal to also 1/8. So we're summing these two. Now, what do you guys notice from this solution? Now you know the support vectors. Where are our support vectors? So the support vectors are the ones that are strictly positive. So it's like, oops. So it's alpha 2 and alpha 3. Alpha 1 was not picked as a support vector. So let's look at this case. So we have these two were picked as support vectors. And the first, the point x1 was not picked as a support vector. Why is that? This is an important question. Why SVM? Why the maths that we defined, that we derived, the algorithm chose these 2 points as support points? There must be a reason. It should not be random because it's all based on mathematical derivations. And it's very kind of, there is an explanation behind this. So I would like you guys to think why I went for this one. So you can see just, here, just looking at these 2 points, they define this distance like it's more intuitive than just selecting these 2, right? Just, to look at the margin. So it's easier to pick these 2 points just by looking at this. They're here, like finding the margin using these 2 points, it seems like more intuitive, right?
Are they the 2 closest points to each other?
Yeah, so yes, very good. So that's a good intuition. So here, if you compare these 2, they are more closer or similar to each other than these 2, for example, okay? So when you're comparing all pairs of potential support vectors that lie on the hyperplanes, okay, on the marginal hyperplanes, yes? Alpha 1 is 0. This is, what we solved right here. So did you get why we got alpha 1 is equal to 0?
But we got alpha 2. We can put it in alpha 1 and we can get value for alpha 1, right?
So here, what we have, just by solving this, right, we find alpha 2 is equal 1/8, but just by plugging this in here, so it's like, negative 16 divided by 8 plus 2, negative 2 plus 2, so that's 0. So numerically, we got a 0 for the alpha 1. And then, am I answering your question? So that's, these are the solutions by solving, the constrained optimization problem using the Lagrangian. So we got alpha 1 equals to 0, which means this is a non-support vector, okay? And then alpha 2 and alpha 3 were different from 0 and positive. So this is a solution provided by the Lagrangian method, okay? Is it clear? Do you have, can you articulate more your question?
Mathematically, it is correct to make alpha 1 0 because we got alpha 2 is 1/8. So if we put it in alpha 1, so we are going to get value for alpha 1. It's not 0. Just go up with it. So this is alpha 1. Okay, if we put alpha 2 and alpha 1, so it's going to be 4/20, right?
But you have a negative here. You forgot the negative. Right, yeah, so.
From my side as well. I thought the minus was at the round of the all.
Oh, sorry, no.
Not on.
Yeah, sorry. So the negative just, for this term. Yes. So if you guys derive it manually, you solve this and you write it down. So I didn't give you time to do it manually, but if you do it manually, the negative is in front, just the first term. Yeah, thank you. Okay? Cool. Now, if we look at this, now we can compute our W. So the W is equal to what? So guys, you can now compute the vector elements, our optimal W star, and also the margin. So let's do this together. So what do we have? So we have alpha 1, which is 0. So you can see that the non-support vector is not included in the W star, so it's completely excluded. So we don't care about x1. But we have y1's alpha 1, 1/8. And then we have y1, which is a negative, so times the vector xi, right? So it's like x2, so minus 1 and 2. And then what else we have? We have alpha 3, which is also 8. And then y3 is positive. And then we have negative 1 and negative 2. And if you guys write this down, what do you get? So if you sum everything, so this is a negative, right? And it's times. So here we will get a 0 for the first one. And the second one is negative half. Okay? If you just compute it, right? And then we can get the margin. So by just dividing, so 2 divided by what? We take the square root because here it's like basically 1/4 times the square root. So it's 2 times 2, and we get our 4. Okay? So that's dividing by the norm of W star. Great. Now, the last step is finding the B star. So to do that, in the last lecture, we saw that we can select any support vector and then just, plug it in. So basically, we selected here point x2, and we have this formula. So we know that y2x, x2 transpose plus b, w plus b is equal to 1, right? So in this case, we're going to get the b. So the b is equal to what? Anyone? So just by looking at the figure, you can guess. But if you derive it, if you write it down, Anyone, guys? Double check. One, two, no. No, not 3, 4. Okay, so you have the W, right? So the B is equal to what? So this is, let's do it together. Anyone got the solution just by doing it? So, right, so Y2 is negative, so this will be here, let's say B is equal to -1. And on the other term, so 1 plus, let's do it this way. So 1 plus x2 transpose W, so that would be, what is x2? Transpose. So here we will have 1 minus 1, that's a 0. Right? So the bias is equal to 0. And you can see it here because it passes through the origin. Right? Okay. Great. So that's it. So you guys now gather all the steps that we need to solve this problem. Right? And now let's look at the intuition. So why SVM? Why not choosing this point x1, instead of x2 as a support vector? So let's look at the intuitive mathematical explanation to this, and this is basically based on the inner product, okay? So if you guys remember, the Lagrangian, the dual Lagrangian, it depends on a pairwise summation of inner products between all training samples from all classes. So let's look at these two cases individually. So the first case is when two samples are totally dissimilar, okay? And this is, for example, right here. So dissimilar means they're perpendicular. So their dot product is equal to 0. Now, if we have samples like that, which means here what we're doing, we're projecting, remember, one sample over the other. So here they're perpendicular, they're completely dissimilar. Their features are completely dissimilar. So in this case, will this impact the maximization of the Lagrangian, these two samples? Will they impact, finding the maximum of this? They're all zeros, right? You're just adding a bunch of zeros. So all those samples that are perpendicular, they do not count. Because at the end, what we want, we know that this is a positive term, okay? So here, ideally, because we're subtracting this term, to boost or maximize the Lagrangian, we want this term right here to be negative, because negative, times negative, it's a positive. So we want to add two positive terms. But imagine that this term is positive, so we're going to subtract it from this, basically if this is positive, then it will decrease the Lagrangian. If this is, negative, right, it will increase the Lagrangian. It will maximize it. So we want to find samples in such a way that this is actually, this sum is becomes negative. So in the first case, when we look at completely dissimilar samples, right, they do not count, because at the end you're just adding a bunch of zeros. So these do not influence SVM. Okay. Now let's look at the more interesting case where we have two samples are very similar. So remember, their dot product is they're almost collinear, right? And so their inner product, they're normalized, it's close to 1, but in general case it means it's maximized if they're not normalized, okay? So here, what we have two scenarios. The first one is that they can be drawn from different classes, okay, these two samples, or they can be drawn from the same class. So if they are, let's say, drawn from different classes, so let's look at how this term behaves, okay? So if we have two samples like that, drawn from different classes, we know that these two, right, the yi and yj, they will always be what? They will be negative, right? Because you're multiplying, two opposite labels. So this term will be negative. We know that the alphas are So this is negative in this case. These will be positive. And we know that they're highly similar. So this is, definitely a positive number, right? Okay. So in this case, this term will be negative. So here, what we're doing, we're boosting the Lagrangian because negative times negative is a positive. So we're maximizing the Lagrangian. Okay. So the dual Lagrangian is being boosted or maximized. So these are actually very good candidates. Why is that? Because their inner product is maximized because they're similar. If they were not very similar, we had something like that, then this will not be, it will be slightly boosted. But if they're too similar, their dot product will get higher, which means this term will get, become larger, and then the Lagrangian will be maximized. So we're looking actually for similar points, but drawn from different classes, right? And these are generally this is the intuition also behind the support vectors, okay? Now let's look at the second case. Right, so in the second case, right here, so what we have 2 points but drawn from different classes. These are what we call the redundant samples, okay? So they're like, very similar. We noticed that if we have 2 redundant samples, their inner product will be maximized, but here, this term will be negative. It will be positive because they're from the same class, which means this whole term will be negative, right? So the Lagrangian, this optimization problem will select some alphas in such a way to penalize this term, to downgrade these samples, right? Because all that we're controlling the alphas. We want the best alphas for this. So this is why for redundant points, generally, the best way to penalize them is to say, I'm going to set them to 0, right? Because you can't give them larger alphas. So this is one way of basically decreasing the influence of this negative term that you're now subtracting from this positive term, okay? So basically, SVM downgrades redundant samples, and it's looking for these, good similar samples drawn from different classes. So now if you look back at this one, what do you guys notice? So the dot product between these two terms, actually the dot product between these two samples is much larger than the dot product between 3 and 1, okay? And that's why in this case, SVM selected points 3 and 2 as support vectors, and it did not go for 1. Okay, great. So now what I would like you guys to do, maybe when you go home, is like to try to solve this manually. So this is a good exercise and training for the exam. So this is, the solution that you should get. So what you can try to find is first compute the W star, so the optimal solution, right? Derive the margin width, and then identify the support vectors by solving this problem. Great, so this was part 1. Now we're gonna look at part 2, which is the kernel trick, and then have a break. But the kernel trick, I'm not gonna do a lot of math. I just want you to understand the concept, okay? Any questions, guys? Is it clear? Yes?
We found the margin was 4, but I saw the distance between the points like 5, because from 2 to 3 was 5, so that's why I said the bias is 1. Am I thinking wrong? Or
right, so you're talking about, so the distance here, if you compute the distance between these two, it should be 4.
It's called.
Okay.
Yeah.
Okay, sorry.
Okay, no worries. Yeah. Okay, cool. Great. So, nonlinear SVM and the kernel trick. So let's look at this case. The question is, let's think about this. How can we separate these two sets using a linear classifier? So you can look at this one. This is actually a genius idea in machine learning. So you look at these two classes, the blue one and the red one, and if you want to separate them, so you know that you need to draw a nonlinear line, right? A nonlinear, like a nonlinear curve, right, in this case. So they're not linearly separable. If like you draw any line, you cannot separate them. You're going to make a lot of mistakes. So how can we potentially use a linear classifier, okay, to solve this problem? So I'll give you a hint. So think about, generally when you remember the first lecture when I gave you, different examples, And one of them was like we can move the points, but we can also stretch the space, right? So we can bend the space in such a way that after, bending this hyperplane, maybe like this plane, right, where all the data points, this manifold where all the data points lie, we can make them linearly separable. Yes?
Polar coordinates?
Sorry?
Polar coordinates.
Polar coordinates. So you basically transform them to a different coordinate. Yes, very good. So that's one possible way of doing this. Basically, you're changing the coordinates, okay, of the samples. What are the coordinates? The features. So what are you doing? You will be transforming the features, okay? So in such a way that you're moving your points around so they become linearly separable, okay? So that's one way. So here, this is the solution basically. So here, we have seen this before, but I'm going to give you a bit more details. So what we want to do, we want to map all samples using a mapping function phi into a new space where they become linearly separable. So in the first case, they weren't linearly separable, as you can see here. But by finding this transformation or mapping function, okay, phi, we map all samples, like the features here. So we're just we're plotting x1 against x2, like just this is the feature space. And the idea is for each point, for example, here, let's say we have this point. So this is my point x. This is sample, for example, xj. So I apply phi to xj, I transform it, and I found this new coordinate, right? So basically, you can think of phi, for example, if you take a polynomial function, it's so easy. If you have your first axis like, 1, 2, then phi of x will be what? Will be 1, 4. Okay, so it's just a simple transformation of features. Now, the key thing is how can we find the phi? That's the thing. So that's the main problem that we want to solve. And look here what we plotted the transformed features, okay, phi 1 of x, phi 2 of x, of the original features in the original space. And in these second plots, what we plotted is like the features against the labels. And you can see that first here, they're like, like they're not very separable by a line, but here it's like more like clear because they gather together, so they're easily separable, okay? So how do we do that? So the first step is to find a good feature transformation phi to map samples into linearly separable sets. So I'm going to give you just an intuition. What do you guys notice here? So when we look at the input space, the original space, you can see that all points, they lie on RD with, in this case, D equals 2. So it's a two-dimensional space. It's a plane. And our points actually are non-linearly separable. But what we want to do, we want to find our mapping function phi in such a way that we're mapping into a higher dimensional space RD plus 1, okay? And here it's like R3. In such a way that all the blue points will lie on top of a hyperplane and the orange ones below the hyperplane. Okay, so we're making them separable, but this in a higher dimensional space. Because here, even if you move them around, so you can move them around in the same, space, right? But it's still, maybe it's more challenging to do that, like to move them around. How can we do that? But I'm sure there are like techniques to do that locally. But in the mapping procedure here process, what we want they become easily separable if we add one dimension.